Hi students, welcome to the class. This is Diksha Kaushal, your chemistry master teacher. And students, as you all know that already our DNA batch has started, right? And today, right, we are going to do the free demo class of DNA batch, right? Right now in the DNA batch, right, I am teaching structure of atom in detail. Every topic is done in detail. So till now we have covered like till Bohr atomic model, right? And out of those, I'm not going to do this class in a sequence. Rather, I will pick out two topics. One is Rutherford atomic model. Second is photoelectric effect. So we are going to talk about these two very, very important models, right? That we will complete in today's session, right? Okay. So everybody, let me know in the chat box if I am clearly visible and audible to you. Yes, students. Going to start for DNA batch students. It has already started, but right now, right, we are giving you one more entry so that the topics that we have done already, that will be covered again. Don't worry about that. But right now also, if you join, there will be no backlogs that will be left, right? Okay. But for the chemistry part, we are doing structure of atom in the DNA batch. Okay. Yes, everybody. Yes. I will teach everything, right? In the batch, everything is going on. Cathode rays, anode rays. Till now, I have taken 5 to 6 lectures and, everything is going in detail only. I have just picked out two topics here from that chapter, right? Okay, yes. So, let us start the session, students, without wasting any time, right? Okay, let us start it. Now, if you talk about models, right? Models, right? Structure of atom, right? First model that we discuss is Thomson model, right? So in Thomson model, what exactly you have? We know that if we talk about a atom, there is a nucleus. Inside the nucleus, there is neutrons and protons, and outside electron is revolving around it. But when there was talk of Thomson model or Rutherford model, till that time, no neutron was discovered, right? They had no knowledge about neutron or nucleus, right? So now all we know was that there is proton and there is electron, right? And the atom overall is neutral, right? That means it is electrically neutral. The amount of positive charge you have is equal to the amount of negative charge you have. So positive and negative charge are equal to each other. So for that, we can say that if you talk about, let's say, I'm talking about an atom here, right? This is a small nucleus, right? And here we are drawing the orbits, right? 1, 2, 3. This is, I'm telling you what we know now. Now we know that there is neutron plus proton here, right? And electron are revolving around it. Electron are revolving around it, right? But at that point, this knowledge was not there. Right? At that point, only we knew was that in an atom, you have two things. One is electron, one is protons. One is protons. Now, electron, right? They are negatively charged particles, right? They are negatively charged particles, and protons are positively charged particles. So, Thomson made a model. He said that it's actually like a watermelon, right? He said that just like you have a watermelon, right? Like this is the watermelon, right? Let us draw watermelon, right? This is the watermelon that you have. And watermelon, the red part is what you eat. He said that this red part is proton. This whole red part is the proton, right? That means he said that the red part that we eat in the watermelon, that is uniformly distributed proton everywhere in the atom, right? And electrons are embedded in it. Like you have seeds. These are the electrons. These are the electrons in the watermelon, right? Like you have seeds in the watermelon, you have electrons that are embedded in the watermelon, right? In the positive sphere of proton. Now he said that atom is electrically neutral. He said that atom is electrically neutral. Now how we got to know it is neutral? right? By doing experiments, we know that atom is electrically neutral. That means the positive charge is cancelling the negative charge. That means electron and protons are equal to each other, right? We know that we have in the discovery, right, we will study about that electron and proton charge are equal, right? That's how, that means the number of electron and proton in a neutral atom are same, and they're cancelling each other, so that the overall atom is in the neutral state. It is uh, electrically neutral, right? So you can see this here, that J.J. Thomson, who invented the electron in year this, suggested that plum pudding model, right? This is little bit English name, plum pudding model. You can say watermelon model, right? Propose that an atom consists of positively charged sphere, like you have red part, electron is embedded in it. In magnitude, the negative and positive charges were equal. Magnitude, negative and positive charges must be equal, and they are opposite to each other. The whole atom is electrically neutral, but Thomson model explained that atoms are electrically neutral. He explained that atoms are electrically neutral, right? Now, what exactly happened here, that he explained that atoms are electrically neutral. Now, after that, what happened? There were so many experiments that were going on, right? Regarding this, just justification was there, okay, that atom is like watermelon model, and with this theory, they were doing different experiments, but this theory was not justifying those kind of experiments, right? That why you are saying that atom, how atom is stable, how this electron that is negative and this hole is positive, how this is embedded in it, how it is stable, how a negative charge which is embedded in a positive charge sphere, how come it is stable, right? So that's how there were so many questions in the mind of scientists, right? Now, randomly, suddenly, Rutherford was not intentionally making this his model, right? He was like, okay, there were some lab experiments going on. Then the workers told Rutherford that there is some unusual thing happening. So now what they were expecting, now here comes the Thomson model, right? So Thomson will be like, can't overfill atomic orbitals if you don't have any, right? So basically he was telling there are different demerits of Rutherford or Thomson that we have. Like we can't have more electrons, less electrons. So all these things were not explained by the Thomson. Now Rutherford will be like, hold, I am here, right? So Rutherford is like, I am about to end his career, right? I'm going to tell you, this you will see in overall chemistry, that one theory and then demerit of that theory. That means the disadvantages of that theory, then you will come up with the new theory. So this will happen, right? Okay, good evening. I'm completely fine. Okay, 12th, okay. Okay. Yes. Now, after this, what will happen? You will have Rutherford here. And now Rutherford, he was not intentionally doing this experiment, right? But accidentally this experiment. Now, what he did, he had these radioactive source in which alpha particles were coming out. Now, can you please tell me what are the alpha particles? What are the alpha particles, students? What are the alpha particles? Alpha particles are, you have helium, right? You take out 2 electrons from helium, that is called the alpha particle, right? That is called the alpha particles when you take out 2 electrons from the helium, right? Now, these alpha particles, we know that now that these are positively charged particles. These alpha particles were coming out of the radioactive source, right? When these were coming out of the radioactive source, these two steps were just to make alpha particles in one line, right? Then this beam of alpha particles will strike on the gold foil, right? Now, question may be, ma'am, why gold foil was used? Gold foil was used because it is a very malleable. It is a malleable metal, right? Malleable means that can be drawn into simple sheets, right? That can be drawn into very thin sheets. That is called malleability, right? Now, he picked up, now gold is a very highly malleable metal. That's why gold was used here. so that we can observe that how alpha particles will behave when they are crossed from the gold foil. Now, what was the expectation of the Rutherford? What was the expectation? Any student here, what was the expectation? Right? Yes, 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 yes. Yes, everybody. What was the expectation from the this experiment? The expectation was very simple. The expectation was that these alpha particles will pass straight, right? This was the expectation, right? But in reality, something else only happened. In reality, what happened is most of the alpha particle passed state, some of them got deflected, and very few, one out of 20,000 got bounced back. Now I'll show you one simulation based on this, right? This is the alpha, this is the Rutherford scattering experiment simulation. Now I'll show you, this is the alpha particle, the radioactive source, right? This will pass through this, and now we will see that what exactly is going to happen. This is the gold foil that we are showing in zoom here, right? We are passing the alpha particles from this gold foil, right? Now we will see what is happening in zoom on the screen, right? Now we will also see the traces, because if you don't see the traces, very small balls you will see, it will be very difficult to identify what is happening. So we'll see the traces here, right? What you will see here, students, that most of the, it's like you have nucleus is like an obstacle for the alpha particles, because alpha particles, if you see, alpha particles are positively charged, right? Nucleus is also positively charged. That means that proton inside the nucleus is positively charged. That is the reason what is happening. Most of the alpha particles you will see are going straight. If I increase the energy here, let's say I'm increasing the energy, more alpha particles you'll be able to see, right? Now, what you will see, most of the alpha particles are going straight. Very few alpha particles you will see are deviating from its path, right? Now, those alpha particles that are deviating from its path, you will see, ouch. Only those alpha particles that are very near, passing very near to nucleus. Here also only that one is alpha, that one is deviating, which is passing very near to the nucleus. This one also passed very near to the nucleus, very near to the nucleus. The one who are passing very near to the nucleus, only those alpha particles are being deflected from their path. Other alpha particles are moving straight, right? There is no deflection in their path, right? Now, I think very few alpha particles, till now I have not seen even one, right? Wait for a minute, we will see something only which will bounce back, right? Because it has to strike on the nucleus to bounce it back, right? Till now, so we can't see anything. Let's increase the atomic mass so that we can see, because more the atomic mass, more is the proton, more will be the bouncing back of the electron, bouncing back of the alpha particle, right? This got bounced back, right? Now this is deflecting. This is deflecting. Let us see which is bouncing back. Till now, so we can't see. This got bounced back because it directly hit the nucleus, right? So that's why only those alpha particles will bounce back. That those who will hit those alpha particles which will hit the nucleus, right? Okay, that thing is clear to everybody or not? Now, if you see, if I minimize the energy, in a slow motion, you can see that very few alpha particles are bouncing back, very few are deflecting, most of them are passing straight, right? If you, let's say, you increase the energy here, right? You increase the energy, you decrease the protons here. When you decrease the proton, very, very rare, because proton is less, right? That means alpha particle is same only. That means the positive sphere inside that atom has decreased. That's why bouncing will be less. When I increase that positive sphere, you will see bouncing will be more. Bouncing back will be more. Right? Yes. Okay? You can see this one deviating. Right? But when you decrease this number, when you decrease the number of neutrons also, Very rare you will see which are actually deflecting or bouncing back. Understood, students? Right? Okay, definitely, Harini, definitely we are going to teach here and on YouTube as well. But definitely, like in a batch, right? Uh, things are little bit flexible, right? Because we have more time, right? We have students who are like, if we take the class, there is a proper set of timetable that is given to the right. That is minimum I am telling you, right? Okay, yes. Now let's draw this. Let's draw this. Okay, so what you have is an atom, right? I'll just draw the atom here, right? I'll just draw the atom here, right? You have one atom, right? Now you have a nucleus inside the atom, right? You have a nucleus inside the atom. Chalo, let's delete this because nucleus will be very, very small. I'll just draw the nucleus like this. Okay, you have nucleus inside the atom. Now, let's see what he observed. Let's see what all he observed. Okay, let's see what he observed. First thing is, he observed that most of the alpha particles are passing straight, right? It is passing straight, right? Can you tell me why? Why most of the alpha particles are passing straight? Because most of the lines inside that, most of the space inside the atom is empty, right? It has no obstacle. Alpha particle can easily pass because this positively charged neutrons are inside the nucleus, right? This positively charged neutrons are inside the nucleus. That is the reason the repulsion of positively charged protons and the alpha particle is less on most of the sides, right? That means, can I say that most of the space, you can just write it here, that most of the space, if I am saying that most alpha particles, you can also do it like this, right? You can just make this table. In this, you can write the observations, right? Observation. And here you can write down the conclusions. And here you can write down the conclusions, right? So what you will see here in the observations part, that most of the space, we are saying that most alpha particles were not deflected. That means most of the space inside the atom is empty. You can write here, that means most space inside atom is empty. Atom is empty, right? Most of the space inside the atom will be empty. Second is, we are saying that only few, or you can say some alpha particles were deflected or deviated. Now, what are these some alpha particles? Let us see this. What are these some alpha particles? They were moving like this. They were going like this, right? Because now they are very near to the nucleus, right? Very near to the nucleus. So that's why they got deflected, right? They are very near to the nucleus. That's why they got deflected, right? That's why they got deflected, right? This is what you will see, that some of the alpha particle got deflected, right? Okay, can you tell me why? Because we can say that, can you tell me why some of the particles got deflected? Because inside the atom there is a positively charged sphere, right, which is located at a very small, in a very small space. You can say positive charge is located in a very small region, in a very small area, in a very small area in center, in the center. That means why they are being deflected? Because in the center there is some positive area which is very small. That is why only some were being deflected. If the area would have been large, then very like high amount of alpha particles would have been deflected. Now, very few, like 1 out of like 1,000, 20,000, 1 out of 20,000 got bounced back. That means the one that will hit the nucleus directly, right? That will get bounced back. Okay, that will get bounced back. Now, can I write it here? The very few, or you can say how many? 1 out of 20,000 were bounced back. Were bounced back. Who will tell me what is the reason behind that? What is the conclusion that you can draw here? Anybody, what is the conclusion that you can draw here? Very good. The mass is highly concentrated in the center of the atom. Very good. The mass is very dense. That means this small positive charge is in small space, but it is so dense that if any alpha particle will strike, it will not only deflect, it will bounce it back, right? So that means the positive charge is very dense, right? The positive charge is very dense, right? So these were the observations and conclusions that you will draw, right? They were passing straight, and only few, some of them were being deflected and very few bounced back, right? So that was the whole thing about Rutherford model. Now, what he called, now if someone asks you who discovered nucleus, before Rutherford model, we only knew there are protons and electrons. Now, Rutherford discovered a new term, that is nucleus. He said that the protons are sitting in a room called nucleus, that is in the center of the atom. And this nucleus is so small, it's like Virat Kohli in the, not even Virat Kohli, it's like cricket ball in the cricket stadium. Cricket ball is very small, cricket stadium is very large. So can you imagine, he is comparing cricket ball with the cricket stadium. That much small and dense is the nucleus when it compared to the atom, right? Okay. Yes, everybody understood? And why this ZNS screen was applied here? Because this ZNS screen, students, this ZNS screen here is actually the fluorescent screen that will blink whenever any particle will strike here, and that will tell you how many particles are striking, how many particles are being deflected, how many particles are bouncing back. Okay? Yes, everybody? Is that clear to everybody? Is this thing clear to everybody, what we are doing here, what we have done here? Right? Okay. Now, shall we start with the theory, like what? According to Rutherford atomic model, the positively charged particles, most of the atoms' small mass was concentrated in minimum volume. Now, beta, if I ask you one thing, chalo, rather than this, chalo, I'll draw one atom here. Acha, tell me what is the mass number? How you tell the mass number? This is an atom, right? This is a very small nucleus inside it. Very small nucleus inside it. Now, how you tell the mass? Mass number. What is the formula of mass number? Right? Mass number. Mass number is nothing but neutrons plus protons. Right? Because after this, now we will also study about Chadwick when we will do the chapter in detail. Right? Chadwick, he introduced neutron to us, and then we got to know that in the nucleus there is neutrons also present. Neutrons were not discovered till not discovered by Rutherford. He didn't discover any neutrons. Nucleus was discovered by Rutherford. Okay, he named that thing that it is called nucleus. Neutrons, he also had no idea, right? But in today's world, we say that mass number is neutrons plus protons? Because whole mass is the nucleus. So whatever is in the nucleus, that will tell you the mass. That's why I just correlated this thing here, right? So you can see here that mass was concentrated in a minimum volume, that is called the nucleus. Then negatively charged electrons encircle the nucleus of the atom. He said that electrons are encircling the nucleus like this. Rutherford also proposed that the electrons move at the speed of light around the nucleus. He named the circular path orbits. After Bohr model, all these things will not be applicable, right? Because Rutherford was not able to explain so many things. What was the drawbacks? Firstly, we should also know the drawbacks of Rutherford, that I'll just discuss. It is not written here, so I'll discuss the drawbacks of Rutherford. What were the drawbacks of Rutherford? Anybody? What were the drawbacks of Rutherford? He said that electrons are revolving around the nucleus. So, we know from the Maxwell theory, what we know from the Maxwell theory? Maxwell theory states that if any particle is accelerated, then it will radiate the energy, right? So we know that because this is an atom, right? This is an atom. If you talk about an atom here, this is an atom. We know that electron velocity is changing direction also. If speed is same, but the velocity is changing at every point because the tangent is changing. So that means this electron is actually accelerated. That means every particle which is accelerated, that should radiate energy. That means it should lose energy, right? So what should have happened? This should have happened that this is positively sphere, right? This is positive nucleus, right? This electron is radiating energy. It will automatically fall. It should automatically fall inside the nucleus. But this does not happen. This does not happen. That is the question mark. That means, see, if this is happening, right? Yes. If this is happening, then me, you, we all are not at all stable. Because in the end, what we are just atom, a collection of atoms who is teaching you about atoms to the atoms. It's like a collection of atoms is teaching the collection of atoms about the collection of atoms. That means I am stable, you are stable, even though we are not mentally stable, but our atoms are stable, right? So atoms are stable, right? So now atoms are stable, then this should not happen. So this theory was against it. Rutherford model was against the Maxwell theory. That will again, when we'll study Bohr model will tell you that there are fixed circular orbits. That's how he will rectify this thing. That is how he will manage Maxwell theory and orbits also, right? Because Rutherford said that there are no fixed orbits. That's why it will spiral, it will follow a spiral path. But this does not happen. That's why this is the biggest drawback, right? Second drawback was he was not able to explain about the line spectrum. Now, line spectrum will be explained by Bohr again. That will be explained by Bohr. This also, beta, we will study in detail what is emission spectra, absorption spectra, all of this we will study, right? Then, he was also not able to explain the chemical bonds. Chemical bond formation. Right? How chemical bonds are being formed. This also Bohr was not able to explain. But still, these were the some things that Rutherford was not able to explain. That's why this model was ruled out. And after this, you will study about Bohr model, right? And you know, it's I can't teach you it in one class. It's itself is a lecture of 2-3 classes. Before this, also we have to study a lot of things, right? Then we will study Bohr model, and it's a continuous chapter. Structure of atom is a very big chapter. right? So I have just given you some part. I have just told you about the Rutherford model and what are the drawbacks of Rutherford model. Rest things, ma'am, what Bohr will tell us about it, how Bohr concluded his model, all of this is a separate thing, right? A dedicated lecture is needed to teach you Bohr model, right? Is that clear? Right, everybody? Okay, right? Clear, students? Now, let us see some quiz. Let's see if you're able to answer this or not. First is, which of the following model of atom describes positively sphere of matter with negative electrons embedded in it? Positive sphere of electrons with negative. This is like a demo session of DNA batch. I have taken when I teach students in the class, right? Uh, what we do in the class is we firstly solve one question for you. Then quizzes will be asked. So you can also ask the DNA students, right? That is done in the class, right? So I have taken only 2-3 quizzes for you because I was teaching you 2 topics in one day, right? Otherwise, in the class, I take 5 to 6 questions for one topic for the quiz, right? So that I'm able to see that whether all the students are understanding. Or in the batch, no, because that is our own portal. So in that portal, we also have the option of hotspot. So like now I have to ask you that are you able to understand this or not, and you have to type yes or no, right? Some of students are not able to tell that okay whether there is any doubt or not. So in the batch, right, there is a hotspot option, right? So in that case, I just ask you, is that clear? Yes or no? You just have to type yes, like click on yes or no. If you're not able to understand, you can put your doubts in the chat box there, right? So I get to know the percentage of students who have understood and percentage of students who have not understood. And in my class, I make sure that there is 100% yes, right? Till I don't see 100% yes, I don't proceed to the next topic, right? So that is about the batch, right? If you ask me the difference, right, that is about the batch, right? Personalized attention is more given. So here the answer will be Thomson model, that is telling you that positive sphere of matter with negative electrons which are embedded in it, right? Then how did the actual results of gold foil experiments differ from expected results? Actual results, how they are differing from the expected result. First is, there was no difference between expected and actual results. Okay, let us see how many of you will answer this correctly. Okay, let us see who is going to answer this. I'll just make a poll here. In the class, so we have quizzes where I ask the students to, answer it. So it is there in the platform, right? But here I have to make the poll. I don't have any other option on here. Let us see who is going to answer this. Let us see A, B, C, D, A, B, C, D, right? Everybody, let us see who is going to answer this. Let us see. I think only one student has answered, or what? So answer is B. Rutherford expected particles to travel through atoms, but instead they recoheted and rebounded, which is unexpected, in the unexpected directions. They bounced back, right? They also deviated. So that was very unexpected, right? So that was the case here. So B is the correct one, right? Then let us see the third one. Rutherford realized that atomic nucleus was positively charged because atomic nucleus was positively charged because how he realized that atomic nucleus was positively charged. I'll just draw it here. This is A, this is B, this is C, this is D, right? Let us see who is going to answer this. I'll close the first poll. I'll start with the second poll, right? I'll start with the second poll. Okay. Let's see this here, right? Okay, let's see this. Let's see this. Why nucleus is positively charged? Alpha particles are positively charged, right? So nucleus will attract it or deflect it. If you are saying that alpha particles are positive, nucleus is positive, how it will be shown? If it is being repelled, it is being repelled. Attracted, not possible. No effect, not at all. It produced alpha particles, not at all. It got deflected, that means it got repelled. So answer will be B is the correct answer. Very good, right? Very good. Now, next topic is photoelectric effect. Okay, so how many of you are ready for photoelectric effect? How many of you are ready for photoelectric effect? And don't forget to hit the like button also, right? So much hard work we are doing just for you, right? Yes, very good, very good. Now, are you ready for photoelectric effect, students? Very, very interesting phenomena. Let us study photoelectric effect. So, photoelectric effect, I'll tell you what exactly is happening here in the photoelectric effect. So, this is one guy, name is Chintu, right? This is one guy, name is Chintu. This is other guy, name is Mintu, right? Name is Chintu. We will understand this with the help of an example that we will see in our daily life. Right? This is Chintu, this is Mintu, right? Chintu and Mintu both are thinking of going to which place? Where you want to go? Where you want to go? Where you want to go, students? Varkala. Varkala you want to go? Right? It's a very beautiful place. Okay? Both are thinking to go to Varkala. Both are as a dreaming of beaches, this and that, will have fun, right? Both are thinking that we will enjoy this and that. Now, Chintu parents are very strict. Chintu's parents are very strict. Now, we have Chintu's parents, right, who are always very, very strict. These are the parents of Chintu, right? Very strict. Now, Mintu's parents are okay. They are like, okay, you want to go, go. But now, Mintu has to convince Chintu's parents so that Chintu can go. Now, beta, if Chintu wants to go on the trip, right? Chintu's parents are not allowing, then he can't go. So, Mintu has to convince the Chintu's parents so that he can get Chintu out of his house, right? So, three things are possible. Can you tell me what are these three things? What are possible? Three things are possible. One thing that is possible is that they will be convinced, right? One thing that is possible is that they will be convinced. So I'll just write it here. One thing possible is that they will be convinced, right? Convinced. They'll be like, Chintu can go out, right? Chintu will go out. Chintu will go. Chintu will go. And Mintu is like, hi auntie, how are you all? I'm the okay auntie. How your best friend convinces your parents, right? How your best friend convinces you. He's like, ma'am, I want to go to AIMS. For AIMS, you don't have to convince your parents, right? For Varkala, you have to convince your parents, right? So, convinced Chintu's parents, and he's like, hi auntie, I am too good. Auntie, don't worry, in Varkala also we'll take our books, right? We'll study in the Varkala also. And you will study on the sitting on the beach. We will study. We'll solve physics, chemistry, bio modules. Like, he convinced auntie to next level that the parents are like, Chintu will go with money. They're like, you go and we are giving you the money, right? Second case is that they are convinced. They are like, okay, you can go, but we won't give you money. Okay, so they are like, okay, you can go. Chintu will go. Chintu will go, but no money. Parents are like, I will not give you even a penny, right? You want to go, you go. We are not making any restrictions here, but we are not even giving you one penny here, right? Third case is, Chintu will like, Chintu can't go. Parents are like, no matter all these dramas and all will not work, right? We were also at your there was a point when we were also we were also kids. We know that you're not going to study on sitting on the beach and you're studying solving modules. This is not going to happen. Chintu will not go. What do you think? What your parents are? This one or this one? A, B or C? If I say this is the A case, this is the B case, this is the C case, what are your parents in this? A, B or C? They will agree or they will not agree? What are your parents in this case? Huh? So now what will happen, right? These three cases are possible. Now I'll tell you in what, ma'am, do we have to do with this in our photoelectric effect? Photoelectric effect is the same. This is the metal. This is the house of Chintu. Chintu is the electron. Chintu is the electron, right? Some light is coming. Some light is coming, right? It will, light is Mintu. Light is Mintu. You can write here, light is Mintu. Light is Mintu. Electron is Chintu. Electron is Chintu. And this metal is foam, right? So now, if light is striking on the metal surface, if it is able to take electron, this is electron ejected, right? This is plus kinetic energy is there. That means electron is ejected with the kinetic energy. Second case possible is electron is only ejected without any energy. There is no kinetic energy. Third case possible is electron not ejected. Electron not ejected. So these are the three cases that are possible, right? Okay. Now let us see this. These are the three cases that are possible. One is electron is ejected with the kinetic energy. Second is electron is ejected with no kinetic energy. Third is electron is not ejected at all, right? So these are the three cases. Ma'am, who will tell us whether electron will be ejected or not ejected? Let's see this, okay? Who will tell you whether electron will be ejected or it will not be ejected, right? Now tell me, when you think that Chintu's parents will be convinced, what do you think that when Chintu's parents will be convinced? What do you think that when Chintu's parents will be convinced? Anybody? Anybody, right? Now, firstly, I'll write the formula here. Formula is students, I'll just write it here. Formula is H mu is equals to H mu naught plus kinetic energy, right? H mu is the incident light. We are talking about incident light, right? H mu naught, we are talking about electron energy, electron. We are talking about electron, right? Kinetic energy is the extra energy that is left, right? Now see this very interesting thing, that when Chintu's parents will be convinced, when Mintu's convincing power is very high as compared to Chintu's parents' rigidity. That means when the incoming electron energy is very high as compared to the convincing power. This is also called the work function. This is called the work function. The energy, the minimum energy required to eject the electron out of the metal, that is the work function. Now when H mu, the energy of the incident light is more than the energy that is required to take out the electron. It's for example, you are sitting right somewhere and someone has given you 10 chocolates. Okay. Now I want you to get out of that chair. If I ask you, I'll give you 5 chocolates. You'll be like, ma'am, what? I'll be not on the loss side, ma'am. You give me 10 chocolates or give me more than 10 chocolates. Only then I'll move out of that chair, right? That means if you have to give greediness to someone, you have to give them something more than they already have, right? So if the incident light energy is more than H mu naught, then the electron will be ejected and the remaining energy will be, that means because H mu is greater than H mu naught, the remaining energy is the kinetic energy. Energy left is kinetic energy. Energy left is kinetic energy, right? Okay, let's say incident light is having 10 energy. Energy needed is 7. So 10 minus 7, you are left with 3. This 3 is the kinetic energy. Is that clear? This 3 is the kinetic energy, right? Okay. Now, let's say electron is ejected only. In this case, Mintu is able to convince Chintu's parents, but they are like, I will not give you any money. That means if H mu is equals to H mu naught, H mu naught. If you have 10, incoming incident light is 10, and 10 is required to take out the electron. So full energy will be consumed. There will be no energy left for the electron to move. That means kinetic energy will be 0, right? Third one, electron is not ejected. That means H mu will be less than H mu naught. Okay, that's why, for example, incident light is having 10 and the energy required here is 15. So it's not possible to take out the electron. So electron will not be ejected in this case. And student, this mu naught is called the work function. Mu naught is called the work function. And this mu is the frequency of incident light. And mu naught is not work function, sorry. This is called threshold frequency. And lambda naught is threshold wavelength. Okay. Bacha, tell me, is there any confusion till here? Is there any confusion till here? Right? Any confusion? Yes, students, is there any confusion till here? Now, I'll just show you what exactly we are going to do here. Right? Now, let us see with the help of this simulation what is happening here. Right? So, firstly, I'll fix one sodium atom. Okay, I have fixed one atom. I'm going to start it, right? I'm going to start it. So let's start it. It is started only, still electrons are not being ejected. That means I have to vary the frequency, right, of the incident light. Can you see? By varying this, what I am changing? I am varying the frequency. I am varying the wavelength of the incident. This is changing. This is earlier yellow, right? It is changing. Can you see? This part is changing. Right, let me just see if you're not able to see that. You can't see that. Wait a minute. Okay, now you will be able to see that. Right. So that is how it is changing. Right. Now, what I'll do here, intensity is 0, so I'll increase the intensity. Can you see now? Can you see intensity is increasing, decreasing, intensity is increasing. Intensity means the light. We are increasing or decreasing. So I'll keep the intensity as 100%. Right? Now, let's see that I have fixed the wavelength at something, at violet. So it is 378 nanometer. Now, I am changing the energy. Can you see? Firstly, we will just see that what is photoelectric effect. What is photoelectric effect? This is the incident light. It will strike on the metal surface, electrons will be ejected and they will move with some kinetic energy. That is called the photoelectric effect, right? That is called the photoelectric effect. Now we will study the graph, right? First thing is how metal plate, this metal, if you change this metal, how the work function will change. Work function means this is the work function. Every metal plate, every atom has its own work function. Sodium will have different, copper will have different. Work function means the minimum energy required to eject the electron out of that metal will be different for every single metal. So now, ma'am, how can you say that we will change every metal? Let's say zinc. Can you see zinc? I have fixed the frequency. Frequency is fixed, intensity also fixed. Everything is fixed. Can you see? With zinc, there is no flow of current. There is no electron that is being ejected, right? Copper, no current being ejected. Platinum, no current. Calcium can eject some currents at this. That means some electrons are being ejected. If you see, calcium is still slow. Sodium is fast. Can you see? Sodium is fast. That means the work function of sodium is lower. For sodium's parents are not that strict. Copper parents are more strict. That's why work function is very, calcium parents are more strict. If you talk about this kinetic energy is slow now. How, ma'am, how this is changing? Simple thing is, beta, if you talk about this thing here, H mu is equals to H mu naught plus kinetic energy. Simple is, if work function changes, I'll just write here, work function changes. How it varies with work function. If the work function is changing, let's say it is increasing, right? This is fixed. This I have fixed. If I fix this, if this increases, this is same. Let's say this is 10. Earlier it is 7. Now it is decreased to 5. This is 10 only. So for this, the energy, kinetic energy will be 3. For this, the kinetic energy will be 5. That means the work function, let's say this is for calcium, this is for calcium, and this is for sodium. That means for sodium, right, less work function is required, less frequency it has, more wavelength it has. That is the reason the kinetic energy is more for sodium. You can see for yourself that sodium, for calcium it is very slow, but for sodium the speed will increase. The kinetic energy increases means the work function is low, right? Is that thing clear to everybody? How if you change the work function, the kinetic energy will change for a fixed frequency, for a fixed incident light. Okay, right? Now, ma'am, let's do other things also. Let's do other, wait a minute. Let's do other variations here. This beta we have already done, right? This also we have done, right? This is the joke that I told you, right? This is what happens when the frequency of the incident light is more. When H mu is more than H mu naught, electron will be like, I have to get up now. I have to go. I can't sleep now. I have to go. I have to run now, right? That's how electron is running from the metal, right? Okay. Now, let's see what is stopping potential, right? Stopping potential is, this is kinetic energy. Stopping potential is Q into Vs. The potential, the external potential that is needed to stop the electron to get ejected out, right? First thing is you are giving the incident light. Okay, let's see this here. You are giving the incident light, you are giving the incident light. It is like the electron is being ejected, electron is being ejected. At one point, if you want to stop it, you will have to put the external potential here. You will have to put the external potential so that you can make it stop. That is the stopping potential. That is called the stopping potential. Now let us see how variation will happen, right? First variation is energy with mu naught. With mu naught, that is the frequency, right? So this is the frequency, this is the energy. Now students, one thing you should understand here, that one photon can take out only one electron. One photon will take out only one electron, right? So if you are increasing, let's say what here you are increasing the frequency. So let's say let's change the frequency. You have a sodium atom I have fixed, metal I have fixed. Now I'll increase the frequency. Increasing frequency means decreasing wavelength. I'll decrease the wavelength. Can you see electrons are moving at a higher speed? Electrons are moving at a more higher speed. So that means when you decrease the wavelength, you increase the frequency, the motion of electron will increase. Can you see that? This is such a fast speed, right? Such a fast speed they are moving, right? If I lower the frequency, if I increase the wavelength, right? No motion. That means, let's see this here. We know that for the incident light, they require the minimum work function to get the electron out, right? Let's see what is that minimum work function. Let's increase the frequency. Wavelength is decreasing, that means frequency is increasing. Increase the frequency, increasing, still no electron. Here, can you see? At this point, when you have green, the electrons are coming out, right? That means this is the work function, the minimum frequency. That is why what you will see here, at this point, there is no kinetic energy. Till you reach mu naught, till you reach the minimum frequency that is required, there will be no energy, no electron. But once you reach this mu naught, then what you will see, as you increase the frequency, speed will increase. I'll increase the frequency. Just focus here. Speed will more increase. As increasing, more speed will be there, right? More speed will be there. More speed will be there. Then more speed, right? More speed, right? That's how with the increase of the frequency, kinetic energy means speed will increase, kinetic energy will increase, because kinetic energy is what? Kinetic energy is half mv square, right? So when the speed increases, kinetic energy increases, right? Okay. Understood, everybody? Is there any problem? Sunshine, sunflower. Any problem here? Now let us see the next graph here. You have light frequency and you have electron current, right? You have light frequency and electron current. What you're going to do here, right? Very simple thing, students. Light frequency, right? Light frequency, everybody. One simple thing is, current means the number of electrons coming out, right? So when you change the frequency, the current is not going to increase. That means, students, that means if you see this here, what I am telling you, that one proton will take out one electron. When you are changing the frequency, right? You're changing the frequency or increasing the frequency, but still one proton will take out one electron only. Even if the frequency of this one proton is more, it can increase the kinetic energy. Frequency will change the kinetic energy, but frequency will have no effect on the number of protons. And current is number of protons. Current is number of protons, right? So as you increase the frequency, number of protons will not increase, right? But as you increase the frequency, kinetic energy will increase. So you can see, by increasing frequency, kinetic energy increase. Number of photon is constant. Number of photon is constant, right? Is this thing clear to everybody? Number of photon is constant, but kinetic energy will increase. Minimum threshold frequency is the minimum frequency required to take out that electron from the metal, right? Now let us see other graph. Now as you increase the intensity, light intensity, right? That means number of photons you are increasing. Number of photons you are increasing. As number of photons increases, but this is number of photon is constant. You can see number of electron ejected is constant. Okay. As the number of photon increases, number of electron ejected will also increase, right? Why? One photon corresponds to ejection of one electron. Let's see how, right? So what we are doing here is we are increasing, let's say, I'll just fix this. I have fixed this here, right? I fixed this here to like violet color. Now I'm going to decrease the intensity. Intensity will be 0. There is no current here. As I increase the intensity a little bit, electrons, 3 electrons, 4, 5 electrons are being ejected. I increase more in frequency, you will see more electrons are ejected. I increase more intensity, more electrons are being ejected. I make it to 100, more electrons are being ejected at this point, right? The number of photons, the number of electrons have increased. Why? Because number of photon have increased, right? But condition is mu should be greater than mu naught. Condition is mu should be greater than mu naught. If mu is not greater to mu naught, let's say I keep the intensity at 100%, but mu is very less. Nothing will happen. No current will be there. So condition is mu should be greater, so that minimum threshold frequency at least we should have, right? Next graph is, you have this thing where you have stopping potential, right? And this is the frequency. Now, simple thing, students, you have, this is the stopping potential, that is Vs, right? This is the frequency. We know that when you want to stop the electron, right? So what will happen? What will happen? This is frequency, this is the stopping potential. As you increase the frequency, what is happening? As you increase the frequency, the kinetic energy is increasing. Frequency increases, kinetic energy also increases. Because frequency is increasing, kinetic energy is also increasing. So to stop that electron, more potential will be needed. That's why potential also increases, right? Understood? When someone is running very fast, more energy, more potential is required to stop them. If someone is running very slow, less potential is required. So when you increase the incident light frequency, kinetic energy will increase and hence stopping potential will increase. But that is only possible after mu naught, right? Before mu naught, there is no stopping potential, because before mu naught has achieved, before mu naught, there is, at this point in this category, there is no electron ejected, right? Your mu should be greater than mu naught. After this, mu is greater than mu naught. That's why only after mu naught you will see that stopping potential will increase. Okay? Okay, everybody. Now, two important graphs, right? Here what you have is, this is retarding potential, this is N. Now let's see what will happen when you change the potential here, right? So I'll just show you this with the help of the diagram here, that will be more clear to you. This is beta the potential, this is right now at 0. I'll change the potential, you will see for yourself. When I'm keeping the potential at, let's say on the positive side, let's say 0.04, right? Can you see? Let me just. Okay. Can you see what is the current? Current is 0.141. Now I am changing it to 0.6, or I will change it to 1 only, right? Current is 0.141. Now I will change it to 2. Current is again 0.141. Now I will change it to 3, right? Current is again 0.141, right? I'll change it to 4. Current is again 0.141. That means when you are increasing the inward potential, you are increasing the positive potential, it is towards the saturation. This is towards the saturation. Now, if you see at 0, can I see at 0? Let's see at negative what will happen. Negative is -2. Okay, -2 we will do, -2. Okay, -2 it is 0. Okay, let's see, you have -3. It is 0. Wait a minute. Let's put less numbers here. Let's put -0.04. You will see the decrement. This is 0.013. Can you see? This is 0.134. Now, when you decrease it further, this is -0.06, right? Can you see current has decreased? When I'll decrease it further, let's keep it to 8. It will decrease further. Let's keep it to 1. Let's keep it to 1. It will decrease further, right? So that means the current retarding potential, when you decrease the potential, right, the current is eventually going to decrease, and what you will see, they are moving backwards. The electrons are moving backwards. They are not coming forward. They are moving backwards. So that is the retarding potential, right? Okay. So this is the curve when you do the experiment, different points you make. This is the curve that we see in this particular. This is a very important graph. Okay. This is a very important graph. Easily they can ask you this graph in the exam. Next graph is this one. Now, here again, this is retarding potential and this is positive potential. Again, it is photoelectric, but right now we are discussing about different currents. Here we were changing the mu. That means here we were changing the frequencies, right? This is very important, that this is the graph that you will see in the frequency, 3 frequencies. But the one which has like over here on the top, that is having the maximum frequency. But in the current, it will change, right? Current will be in this side, it is after 0, it is increasing and then it will start decreasing. Here it is decreasing only, and here I1 is greater than I2 is greater than I3. When we talk about the current, the number of electrons that are being ejected, right? Okay. So that was about these two graphs. This graph is again very important. This is also again experimental data graph, right? You can also consider this graph. Now this is potential, right? When the potential is stopping potential is Vs, right? After this stopping potential, we are talking about when you try to stop the current. Let's say this is 0, this is Vs, this is the stopping potential. Before reaching the stopping potential, there will be some current, right? So when you are moving, when you are increasing the potential, right, that current will firstly increase, then it will decrease. When you're moving towards the stopping potential, it is going to obviously electron will stop. That's why current will decrease here, right? Okay. So I think that's it, right? Rest of the part, if you want to do, you let's do. If you don't want to do, we can skip that also. You can let me know if you want to do questions, because the questions I have picked out from JEE, right? Reason being because you know that your level has definitely increased, right? So we'll talk about only those kind of questions where level increment will be there, right? So let's talk about this first one, that is in the batch, we are not only teaching you the NEET previous year question, we are teaching you other previous year questions that are needed for you, right? The when light of frequency twice the threshold frequency is incident on the metal plate. Now there is some frequency mu, right? This is incident twice of the threshold frequency is incident on the metal plate. The maximum velocity is V1 when the frequency of incident radiation is increased to 5 times. When this is 5 times of mu, that means it is 10 times of mu naught, then the velocity is V2. Okay. Now, here what you will see, they are asking you V2 is equals to X of V1. Simple thing, how you will do this. We know two formulas here. We know two formulas. One is H mu is equals to H mu naught plus half mv1 square. Here H mu is nothing but 2 mu, so it will be H 2H mu naught, right? This will come out to be 10H mu naught. This is H mu naught. This is half mv2 square, right? So now what you will see, it will come out to be H mu naught is equals to half mv square, v1 square. This is 9H mu naught is equals to half mv2 square. Half will cancel, h will cancel. This will be, division will be, this will be v1 square by v2 square, right? This will be 1 by 9. So v1 is equals to, or you can say v2 is equals to, v2 will be this side, 3 of v1, right? That will be the answer. That means x is going to be 3. That means this x value is going to be 3. Okay? Okay, students. Now, let us see one more question based on this, right? That is also a very interesting question, right? Because the level is going to increase, so we have to just by, okay, ma'am, there was this formula. We just know how to put the formula. Rest of the things we don't know. So, level will definitely increase. So, you have to do different types of questions. The work functions of some metal is listed below. The number of metals which will show photoelectric effect when light is 300 nanometer. Now guys, here what you have to do, they are giving you the incident light. That means H mu you will calculate here. We know that energy is equals to 12400 divided by lambda. If you are calculating this, then lambda value should be in Armstrong, and that's how you will calculate this value in electron volt. Firstly, convert this into Armstrong. Convert this into Armstrong. Then put the lambda value here in this formula. You will get the energy value in the electron volt. Now, those energies which are greater than this value, that means, sorry, this is the work function. No, yes. Those energy which have value less than this, right? So let's see, energy is coming out to be this one. Okay, this is the energy of the incident photon, right? This is the energy of the incident light. So we know that this energy should be greater than the work function. If the work function, this energy, that means if you talk about, let's say 2.4, this is the work function, right? You have incident light is 4 point something. Incident light is coming out to be 4.14. Right? This is energy of photon, or what will show the photoelectric, wait a minute, the number of metals which will show photoelectric when the light of this wavelength falls on the metal. So this is incident light only, right? That means this is the energy of the incoming energy. So E should be greater. This energy should be greater than the work function. It is greater for this one. It is greater for this one, for this one, for this one. This is not greater for this, this, and this. That means, can we say that photoelectric effect energy of this should be greater? Hence, only lithium, sodium, potassium, magnesium will have work function less than this. So, only these will show the photoelectric effect, right? Okay. So, guys, that's it about the photoelectric effect and the Rutherford model, right? Now, DNA batch, like the demo class, this was a demo session of DNA batch only, right? So, this demo session we have, right? We have discussed whatever we have discussed, same or more will be done in the DNA batch, right? Because the concentration of students are more, right? Students are more involved in the class, right? Here you can see the involvement, seriousness is very 0 level only, right? Distractions are very less in the batch, right? Total focus, every student sitting there, right? When you give something, when you give money, right? Money is also not that much, but still it is hard-earned money of your parents, right? So when you give some money, you know the responsibility that if I am in the class, I have to study, right? And students, what is the best thing is that we take live classes in the class. We have quizzes also in the class. You will have leaderboards also. You can see the competition there. You can ask your doubts. And you know what's the best thing? I also make the class private sometimes, right? Private means not the class, that means the chat privates. I also have the, in the class, teacher has the option to make the chat private. Now, for example, you are getting, like you want to ignore the chats. You don't want to see the chats, right? I'll make the chats private so that you are not able to see each other's chat and you only focus on the class. Sometimes I also make it public, right? This session is variated among these things, right? And next important thing here is that everything is live, so you can ask your doubts in the class, right? There's a class teacher who can also answer your doubts, and I am there only to answer your doubts. The teachers are there only to answer your doubts. Next is, after the class, if you have any replay version, then also you can ask your doubts in the replay version as well. For example, you have missed your class because of something, right? Now, previous year questions will be solved in the class. Not only I am talking about NEET previous year question, I am also talking about JEE previous year question, because that is also needed at this point, right? You never know which previous year question will be directly asked, right? Then in class quizzes will be there, leaderboard will be there. Practice question, for that DPPs will be provided to you. DPPs will be provided to you. Not only the DPPs, but also you can generate your own DPPs in the class for any topic you want to, and defining the complexity level. And We will also give you the Tattva modules where you can tick out, okay, these are my questions that I want to do, right? And we will also give you some questions for your homework that are must to do from that topic only, right? Then this price is only 4,999, right? And you can see where to find this. You can see on the in the description box here, right? You will see this DNA NEET batch 2026. You can just click on this and you will see the link here. All the features I have already told you. Plus, I forgot to tell you the mock test, right? Every 15 days, there will be mock tests that will be conducted based on the syllabus that we have completed in those 15 days in the batch, right? According to that, things will go, right? Yes, DNA batch has started, guys. I have around 10-15 classes we have done of like not for every subject, combining 10-15 classes we have already taken, right? 5 classes each subject till now we have taken, right? Okay, so that's it for today, students. You can decide for yourself, right? I would advise you to get enrolled to DNA batch because the sessions are really, really amazing. You can ask the DNA students as well, right? The discipline that we have in the class is next level. There is no distraction in the class, right? Every single student in the class is completely focused. There is that competitiveness within the class, right? Yes. Okay. Chal. Okay then, students. Then bye-bye. Take care. See you all in the next class. Bye-bye. Yes. Chal. Okay then. Bye-bye. Bye-bye.